Okay, let me switch over to this one. There we go. I am picking up with lecture 5 then, which is going to take us a while to get through, but that's okay. So this is corresponding to chapter 5. This will also be the topic of your next homework assignment. So I will have to look at where we are with this in terms of the due dates to see if I need to adjust anything. But I'm happy to slow things down so that we understand things better rather than rush through it and feel like you're lost. So we will make it work regardless. Okay, stop that. I lost my mouse. Come back. There it is. Okay. Hide meeting controls. I'm at the point where I have to narrate to myself what I'm doing. And I lost my mouse again. You'd think having a giant pink mouse would be enough, but no. No, seriously, it's like a ghost mouse. Everything is flickering. Is there a keyboard shortcut? Okay, oh, I found it. No, really. Okay. You're going to see Lisa throw a fit with technology.
So I usually that's happened to me. I don't know if you have a Windows or a Mac, but it happens to me on my Mac, and I take a screenshot and somehow that usually does something. I don't think there's any logic to, oh wait, but it did.
Okay, but then it disappears.
Yeah.
Okay, well then we're just going to do it out of the full thing here because I'm going to lose my mind otherwise. Hide meeting controls. Okay, there. Advance the slide. We got it. We're going to make this work. All right, so modeling change versus fluctuation. Oh, I can do it up here. My mouse is working up here. From current slide. Yay! I win. I win, technology. Take that. Okay, so we're changing gears, heading to the other side of the picture here. Within person change. So you are about to now transition into the world of what is known as growth curve modeling, or latent growth curve modeling if you want to sound fancy. Even if your change trajectory is not growing, and even if it's not curved, it is a growth curve model. It is also, you can use, if you want to sound extra fancy, so like if you're in a job talk, it is examining inter-individual differences and intra-individual change. And you think I'm making this up, but you will read this kind of stuff in papers and it sounds super fancy. It's not. So I'm here to demystify that for you. The main idea is that we are going to examine what kind of change happens on average. So if we plot like the means over time, what are they doing? Are they going up? Are they going down? Do they start going up and then come down? There's all sorts of possibilities. That's what's going to be the role of the model for the means. Fixed effects, average change. What do we got? What is the shape of the trajectory on average? How do we model that? In the model for the variance then, we are going to be asking which aspects of that change trajectory do each person need their own version of? So do people change at different rates? That's the question. So we've talked about the idea of a random intercept up to this point. The gesture I'm going to make to go with this, see Jordan, you can see it live today. Isn't this exciting? This is a random intercept. So this hand gesture is random intercept. It's my way of saying like a shift on Y. So like this picture here has a random intercept because people differ from each other in their average outcomes. But this picture also has what's going to be known as a random slope. The idea that people need their own version of the fixed slope. So that's the main difference, is that we're going to have more things become random than just the intercept in this approach. What it is secretly doing though behind the scenes is the same thing as the models we just finished. It is predicting a pattern of correlation. Random slope models predict that variances change over time in a particular way and that covariances change over time in a particular way. So it's another set of options for how we describe the total pattern of variance and covariance across occasions. All right, so choices then. Model for the mean side, what happens on average. Model for the variance, concerned with individual differences. First, the mean side. You only know two choices so far in terms of how we would describe change over time. You can have an empty model, which means there is no change over time. You estimate the same fixed intercept across all the occasions. Or you can have a saturated model, where the word saturated means you have spent every possible parameter that you could with respect to time. So if I had 5 occasions, a saturated model has 5 parameters. It would have an intercept at one occasion and 4 differences. That's ANOVA. That's the idea of treating time as a categorical predictor. That's what saturated means. That's not always possible to do. So saturated means models are not possible if not everybody has the same set of occasions. That's what's known as unbalanced time. So if some people came in late or early and they have a different time value, that's not necessarily a problem. You want to leave it that way. It just means that you might not be able to have a distinct mean for every possible value of time absorbed in your data set. In that case, you might want to round into convenient intervals just to make some pictures to try and get a sense of what's going on. But where we are headed then is intermediate choices. So again, with Name That Tune as my idea, we're going to play Name That Trajectory. What is the trajectory like on average, and how do we estimate fixed effects in the model for the means to describe it? That's what we want to know. Questions. When I say empty means there is still one parameter estimated, the intercept? Yes, the fixed intercept in particular. So it is empty with respect to no time predictor being included. Empty models always have an intercept, a fixed intercept at a minimum. That just allows the total mean for the outcome variable to deviate from 0. Okay, with me so far? All right, variance side. Same picture as before because we're doing the same thing as before. We're trying to find something in between compound symmetry as the most parsimonious, simplest model we would entertain for longitudinal data. That says that people differ from each other only in their intercepts. Everybody changes the same. On the other side is unstructured. Let it be what it wants. Each occasion gets its own variance. Each pair of occasion gets its own covariances. The models that we will entertain that allow individual differences in change, so people get their own intercepts and their own time slopes. So new gesture, this is individually varying time slopes here, or this arm. Those actually predict patterns that are in the middle. So we want to see to what extent we can approximate this unstructured matrix with fewer parameters through the use of random effects. So letting people have their own version of the time effects creates a pattern. Just like AR1 created a pattern and Topolitz creates a pattern. It's another set of options. All right, so back to where we were in the world of within person ANOVA, the empty model. So the first thing that we will do in any longitudinal analysis is estimate what is known as an empty means model, where we have a random intercept variance and we have a residual variance. So again with the terminology, the level 2, that's between person, that is inter-individual differences. The random intercept U right here is how far off each person's mean is from the grand mean that's given in red here. So U describes why you are systematically higher or lower. U sub 0 is meaning that it's an intercept specifically. And the I subscript represents that each individual gets their own. So it's 1 per person, not 1 per occasion, just an I. So this, the variance across people in their U's, that is tau squared by convention. Somebody just decided that that's what we would call it, and I'm following that notation that's pretty much everywhere. But when I write this out, I always use a subscript for what it is the variance of. So the way to read this is that because it's a tau, that's a level 2 variance of some kind, it is the level 2 variance across the U zeros. So that describes how people differ from each other in their means. That's what level 2 random intercept variance is. And which matrix does it live in? This can be a finger question or a typing question. Which variance, or which matrix does the level 2 random intercept variance live in? Yeah, G. G, very good. So you can think of this as the part of the data that would have been there if you just did a cross-sectional study. People differ from each other. Yeah. In a longitudinal study, people differ from each other in their means, usually at a minimum. From there, once we have given each person their own mean by giving them a U0, E is the difference between what they had at a particular occasion and their person mean. So E has a TI because E is per time per individual. And we usually assume that the variance across times and persons is one number. We don't have to, but that's what this model is predicated on. And so by convention, the E's have a variance this is sigma squared. So this is the same notation that's used in linear regression, where we had an E at the end of the equation and its residual variance is sigma squared E. So level 1 is E variance within persons, intra-individual variation, the longitudinal part, and then level 2 is between persons in U. And where does E variance and its covariances live? What matrix? R, yes. And when you put them back together again to describe the overall pattern, what's that called? What matrix is that? V. V for victory, because I finally understand this crap. You have no idea how long it took me to figure this stuff out. I'm still figuring it out, to be fair. But this part in particular, how G and R and V work together, that threw me for quite a long time. So welcome to your very first multi-level model. It's a new system of notation. Yay, I see some clapping. I know, it's exciting. So we're changing the notation. It looks silly when you only have an empty model, but it will make more sense as we go on. So we're starting with, this is a point of reference here. This is what an empty means model would look like in the GLM. So those of you who took 6242 with me, I made a point to show you this because I knew this was coming. The empty model gives you back the mean of the outcome and the variance of the outcome. From there, you add predictors to try and reduce that variance. So in GLM notation, in which there's only one outcome per person, that's why it's Y sub I and E sub I. So those are variables. Beta 0 is a constant. It doesn't have an I because everybody gets the same beta 0 fixed intercept. I am using a color coding scheme, by the way, throughout these slides to try and help you keep stuff separate. Parameters in the model for the means are going to be red, and parameters in the model for the variance are going to be blue. So beta 0 is a fixed intercept in the model for the means. The variance across people in the E's would be the residual variance. That's in the model for the variance. So we are switching our system of notation to break down the model into two different levels. So in a longitudinal analysis, now we're predicting YTI, Y per time per person. So that is a data structure in which each row is per occasion. So that means I need an ID variable for which person is which, and I need an ID variable for which time is which. So all the Y's are in one column. The first thing that we encounter is beta 0, but beta 0 is no longer a parameter. Beta 0 is a placeholder. Beta 0 is like a backpack. It holds things. Because each person is now going to get a different beta 0. It has picked up an I. What beta 0I is how each person is going to get their own intercept according to the model. Given that I have no predictors, the intercept is the mean. So then we come up to level 2, where beta 0 I is itself an outcome. And now we say how each person gets their own intercept with a combination of fixed effects, which is what is for everybody, these are constants, and random effects, which is specific to you. Everybody gets their own, is a random effect. So this Y looking thing right here, this is our new friend gamma. I'm not using the equation editor in most of these slides because it makes it the format huge and very unwieldy, so I'm just typing this using the equation symbols. But so it'll look a little bit different, but gamma looks like either a Y or a V depending on your font, but it is not Y. So note, this is what Y looks like in my font, and this is gamma. So gamma 0, 0 is the fixed intercept. It is a constant. It is the parameter in the model for the means. U0I is the random intercept. It is how far off from the mean of the person means each person's intercept is. So gamma 0, 0 is the mean of the person means. U0 is how far off yours is, where each person gets their own. And together, they get you to where the person's mean is. Then we come back down to level 1, and we pick up ETI. So E is the level 1 residual at time t for individual I. It is how far off a person is from their mean at a particular occasion. So this seems hella convoluted when you come over here and look at the composite equation down in the lower corner. This is what I have, 3 things. So in parentheses is what beta 0 I represents, the fixed intercept plus the random intercept. What everybody gets plus how I deviate from the average. That's my intercept. And then E is how far off I am at this occasion from my intercept. So in terms of what is actually being estimated, the model will spit out a fixed intercept estimate. That is a fixed effect. So we get that in the model for the means. It will also estimate the variance across people in the level 2 U's. So that's my random intercept variance. That lives in the G matrix. That describes how much people differ from each other in their person means. This tau squared U0 thing. Then we also will have an estimate of the level 1 residual variance, how different people are from their means over time. So that is purely within persons. And these two sources of variance are uncorrelated. So in multi-level modeling, like the definition of what is a level is that it is a separate thing. So the level 2 observations and the level 1 observations are uncorrelated. So we've broken down the total variability into 2 sources of variance, 2 piles. Between person, level 2, random intercept in G. Within person, level 1, residual variance in R. Okay, how we doing? So my choices for notation, by the way, are largely almost completely driven by my ability to be able to write these things on a chalkboard. Because when I first started teaching, that's what I had to do. I would have to get out the whiteboard and start writing these things down. So other sources will use different notation. In particular, U's are often referred to by the Greek letter that I call squiggle 1. I'm not sure what that is, but that's what they usually use. And some sources also use pi for the betas, like the Greek 3.14. And I can't handle that pi is not 3.14, so I don't use it in my notation. So this notation maps onto what is used in sort of clustered data multi-level modeling more directly, but I think these terms are a little bit friendlier and easier to remember. Can I repeat the uncorrelated level thing? Yeah. So if you have a variance component at a different level, by definition, it is uncorrelated. So the E's have nothing to do with the U's. So you can add them back together again to directly get a total variance. So this is a compound symmetry model that we're talking about here, where the total variance is part E and part U0. You can add them back together again because they're uncorrelated. Okay, other questions? So saturated means model, what would that look like in our new notation? Well, if I had, say, 4 occasions, a saturated means model would treat time as a categorical predictor, and it would estimate an intercept for one of the occasions, and then a dummy code basically distinguishing each other from that reference intercept. So if I use the way that SAS does it, for instance, the highest value is the reference for categorical variables in SAS, so that would be time 4. So my level 1 model, if I were to estimate a saturated means model, would look like this, where time 1, time 2, and time 3 are binary predictors, distinguishing time 1 from time 4, time 2 from time 4, time 3 from time 4. So I would have a potential beta for each of those that each person in theory could have their own version of. To keep it a random intercept model, though, I would only have one U here. So as many betas as I have in a level 1 equation, I have that many level 2 equations. Each beta holds, as a placeholder, how an individual gets their own of a particular parameter. In this example, the latter betas, 1, 2, 3 here, are only given fixed effects. So this model says that we can have mean differences over time, but everybody has the same pattern of mean differences. So this is a model that says people differ in level only, not in change over time. Because the people differences are the blue part. There's only a random intercept. So putting it together, it would look like that, which is how we expressed when I was talking about ANOVA language, I used composite notation because it's simpler to explain than that. All right. So, questions so far? All right. So reminding you how these things get put back together again. So what is going on under the hood when you specify a model that looks like this or a model that looks like this? They have the same model for the variance.
And I think I have a question.
Okay,
real
hit
quick.
me.
So what we were doing before wasn't a multi-level model. Is it because we only had a random intercept? I guess I'm getting confused, like why that isn't considered an equation in and of itself.
It is a multi-level model, but I wasn't
Okay.
describing it with multi-level model notation.
Okay. Okay. So it is a multi-level model though, because I was like, but there is 2. Okay.
Yes, so this is just taking the ideas that you already have and putting a new set of notation on them that's going to allow us to expand what is possible.
Okay.
That's the objective. So that actually brings up a point I was going to make. Let me back up for just a moment here. This slide here is slide 4, talking about sort of the ends of the spectrum in terms of possibility. I had people ask me questions before, like, if I have only 2 occasions, or if I have only 2 people in a group, like if it's dyadic data or something, like what should I do with that? Should I do a multi-level model? And my answer is usually no, just do a multivariate model. And they're like, what do you mean? This is what I mean. If I only had 2 occasions, then this unstructured matrix right here would only have 3 possible values. I'd have a variance for the first occasion, a variance for the second occasion, and 1 covariance between the 2. If I only had 2, that's what I do. Because it can't be wrong. If someone says, no, you shouldn't do a multivariate model, which is what this is over here, you should do a multi-level model, then they're saying, no, you should do it this way, where each of these variances is predicted to be part U and part E, and the covariance is predicted to be due to U. That has the potential to be wrong. Because to the extent that the second occasion's total variance is different than the first occasion's, putting in a random intercept is not going to capture that pattern. So this idea of just directly letting the residuals at each occasion have their own variance and their own covariance is what I would call a multivariate model. If you include a random intercept to try and predict that pattern, then it gets called a multi-level model, but it's really a semantic distinction. So the problem with the random intercept only model is that it is a compound symmetry model. And to the extent that your two observations have different variance, it's not going to pick that up. So you may as well just do this over here and leave it as unstructured. I would give the same exact advice, by the way, if you're doing any dyadic data analyses. Does anybody have data like that they play with? No? Okay, so in dyadic land, there's often people who talk about doing multi-level analyses with dyadic data versus path models or multivariate. I would do it this way. I would do it as an unstructured. I would not use a random intercept, because then you would have, like, you know, the mom's variance and the kid's variance, and then they have a covariance. Or, you know, the spouse's variance and their partner's variance and their covariance. You don't need a random intercept to make that pattern. So all of these are multivariate models. There is a multi-level way of putting the pattern in that is helpful if you have lots of data. It becomes less helpful if you don't. So yes,
Okay.
we've been doing multi-level modeling this whole time.
Now I think I'm just getting confused about what's multi-level and what's multivariate.
They're synonymous.
Okay.
I mean,
Okay.
they are. It is a semantic distinction. The term multi-level usually refers to structures that try to break this overall matrix into levels as a way of
Mhm.
patterning it. I'm making it worse. You can also have multivariate multi-level, by the way, which
Oh
is
gosh, okay.
multiple outcomes over time.
Okay, so I thought multivariate meant multiple outcomes.
It does.
Okay.
Because I've got a time 1 and I've got a time 2 and I've got a time 3.
Okay.
So from that perspective, it's the same thing.
But
Multivariate,
multivariate,
yeah, multivariate,
oh,
multi-level would be both.
but you can have multi-level without more than one time period, right?
In this context, the multi-level nature is because of multiple occasions within a person.
But if it was clustered or whatever, it could be. Okay, okay.
In clustered data, then what is being measured multivariately is the cluster.
Oh gosh.
And then people are the occasions.
Okay, I'm just making it worse.
Yeah, I'm making it worse. There's a lot of confusion because of the terminology. But at the end of the
Mhm.
day, what we're trying to do is predict a total pattern of variance and covariance across occasions or across people from the same group. Both of those things are true. The approach that you take in doing it then gets called different things. If there's not a random intercept in the model, I wouldn't call it a multi-level model per se, although other people would.
Okay.
Question on slide 7. Is slide 7 a repeated measures ANOVA with the between person variance added to the time for intercept? So yes, this depicts a univariate repeated measures ANOVA. That's what this model notation is. And the random intercept is in the line for the beta 0 because they have to match. So beta 0 here is a placeholder for how each person gets their own intercept that happens to be at time 4. But the fact that there's only a U0 in the model means that they would be parallel differences. So U0 is just a constant. You could stick it in, you can't stick it anywhere, but when you put it into the combined notation, it just adds a constant shift to people's scores. So this beta 0 intercept is the place where that would happen. Otherwise, if we put U's in these other equations, that would allow a differential shift at those occasions between persons. And that's not what this model is saying yet. Other question, does number of time points play into whether I would specify a random slope model? Does a random slope model make sense with just 2 time points? Great question. A random slope model is not possible with 2 time points. You got to have 3. Not everybody has to have 3, but at least some people have to have 3 for it to be estimable. Because if you only have 2 points for people, the line is going to fit it perfectly. So if you only have 2 occasions, you can either give each person their own slope, or you can have a residual variance left over, but you can't have both. They're the same thing. So 3 is the minimum to play. All right. So either way, if you only have a random intercept, the pattern that you're predicting in terms of the total overall variance and covariance is compound symmetry. So I just wanted to make that point again. And the intraclass correlation shows up in VCore as a ratio of our between-person variance over total. So that can express how much of the variation is due to between-person differences as opposed to within-person variation over time. So that would be the first thing that we calculate is the interclass correlation. So do you remember interclass correlation? The lowest that it can be is what number? This is a finger question. Yeah, 0. What's the most it can be? 1. And what value of interclass correlation means game over for your longitudinal analysis? Is it 0 or is it 1? It's 1, yeah. An interclass correlation of 1 means that all of your variance is between person, none of your variance is within person, meaning you do not actually have longitudinal data. So an interclass correlation of 1 is a deal breaker with respect to longitudinal analysis, but anything under that, play ball. All right. So now we can start talking about time with the preliminaries. So we're going to do growth models, right? That's the objective here. And in thinking about what needs to go into the model, there's 2 sets of decisions that we have to make. What goes into the model for the means? What goes into the model for the variance? On the mean side, is there an effect of time on average? Do we need fixed effects of time? Fixed effects of time are a common slope that's going to apply to everybody. That's the minimum that you would expect in terms of growth curve modeling in most cases. The part that we have that's extra, that's available to us so long as we have 3 or more occasions, the part that ANOVA doesn't do is this idea of, does each person need their own change over time? In which case we would say that they need a random time slope. So in terms of vocabulary, fixed is the part that everybody gets the same. Random is the part that you get your own version of. So I also like the notation of use for random effects because it's like, it's for you. It's yours. Random is yours. So to illustrate these possibilities then, here is what it would look like if I have an x-axis here that's some sort of time metric. The y-axis is my outcome. The black line is the trajectory through the means on average for the sample. And these individual lines would be trajectories through individual people's data. So this picture illustrates a data set in which we have neither a fixed effect of time nor a random effect of time. I say we don't have a fixed effect of time because on average, this heavy black line is flat. There is no change on average. So that's no fixed effect of time. There's no random effect of time because everybody, no change is the same. So random means everybody needs their own. In this case, that overall line holds equally well for everybody. So there is no random effect of time. If I just give everybody the same line, that's good enough. Here's a picture that shows a fixed effect of time without a random effect of time. So now what's happening is that on average, the line for the sample means here, the heavy black line, is tilted upward, so people are growing over time, but everybody's growing at the same rate, so we don't need a random effect of time. Everybody doesn't need their own slope. So the intercept is random in every picture. Everybody gets a different mean. And in this case, everybody grows at the same rate. And these are the only two pictures, by the way, in which a univariate repeated measures ANOVA or a compound symmetry model or a random intercept only model, take your pick, will fit. Because what a random intercept compound symmetry univariate repeated measures ANOVA model says is that everybody changes the same. That there's only one way that people differ from each other in their intercepts. That's it. That implies parallel slopes. Because that's the only way that the total variance, like if you think about the cross section here and here and here, the total variance is staying the same across time. The only way that can happen is if there's parallel lines. Okay, with me so far? Look, my mouse is back. It heard me getting angry. So here's probably the most interesting case, and yes, this is possible. You can have not a fixed effective time, but a random effect. So I say that on average, there's no change. But that doesn't characterize individuals because they are averaging out. Some people are increasing and other people are decreasing. So this can happen if you were to say, collect data for a dissertation. You worked really hard to collect longitudinal data, and you go home and you run your repeated measures ANOVA model, and you find that there's no main effective time. There's no change on average. And you might want to cry because you have no results. But if you made a picture and the picture looks something like this, then you shouldn't cry, you should get very excited. Because this is a much more interesting story. Let's say that the objective of your dissertation was to try out a new procedure that's supposed to make people better. Well, did it? Some of them. Some of the people grew over time, but some of them got worse. So then that introduces the question, okay, why did some people get worse? What is it about them that this treatment not only didn't work, but made them worse? So being able to predict why people need their own slopes. Yes, there is a random time slope here. Why is that? That's the purpose of the model. And we can predict why people need different slopes with person level characteristics. Why is it that some people did not respond as well? Is it their age? Is it their gender? Is it their personality? Is it their political affiliation? Is it something that has been measured one time or something that is constant to a person? That would predict why some people change differently than other people. And a consequence of having random time slopes, like in this picture down here, is that the variance changes over time. There is less variance earlier in the study than there is at later occasions as individual trajectories spread people apart. So the model has to be able to include that as part of its pattern, that the variance grows over time. Random slope models predict changes in variance. They also predict changes in covariance, as we will see. And you can have both. So you can have average change in one direction, and you can have individual differences in the extent to which that's true. So you can think of these as like a 2x2 continuum here, where you can have one, either, neither, or both. So just because you don't have a fixed time effect, for instance, doesn't mean that you can't go looking for a random time effect. You can have any combination of this actually happen in real data. Okay. Yeah. Pictures. Okay, are you with me so far?
When you said there's not a main effective time, looking at the bottom left-hand corner, it's because, okay, so is the for example, the upper right-hand corner, that is a main effective time because everybody is going the same direction, so time is significant there.
It's a main effective. Let me stop you. It's a main effective time because of the slope of the heavy black line. Not because everybody's the same, okay. It's the slope of the heavy black line. What's happening on average is what a fixed effect is referring to.
Okay, so if I did my dissertation and we talked about how we might cry at first getting the bottom left-hand corner, but when we look at everybody separately, it's like a good thing because we can kind of figure out why they're differing. On the other hand, it's important to look how everybody's different. So those within person, and then
Yeah, I don't have within
that I would
person
be happy in. I'm
variation.
comparing the, okay.
So you would picture like little dots around these lines that these lines are traveling through. So these lines are sort of
Uh-huh.
like projections through the data, not the exact data.
Okay. Okay.
But yeah, like if this was your picture that came out of your dissertation, you fixed everybody. Hooray! You win.
Yeah, and if you got the upper left, it would be awful, right? Because it's like nothing.
The upper left is a picture of an interclass correlation potentially of close to 1, right? Like all of the
One.
action
Yeah. Okay.
is cross sectional. You wasted your time. Yep.
Thank you.
Sure. Question, so how does this differ from like a time interaction with certain characteristics? That's exactly what it's going to take. So what's going to end up happening is that if you have a hypothesis that, say, people in the treatment group improved, but people in the control group got worse, the way that you would test that hypothesis is as a group by time interaction. That becomes a fixed effect in the model that allows the effective time to differ between groups or the effective group to change over time. So the latter, like if you look at the left-hand corner down here, right, if random assignment worked, everybody should be kind of like the same, and then they spread themselves out. So the effective group would change over time, or the effective time would differ between groups. That is known as a cross-level interaction because time is a level 1 predictor and group would be a level 2 predictor. So those sorts of cross-level interactions would explain why some people need a different slope than other people. And so what's going to end up happening if you had a picture that was either of these bottom ones here is that we're going to add a third type of variance to our model. So we already had individual differences in intercept. This, why do some people have different means? We also had within person level 1 variance around those means. We would take part of what we called within person level 1 variance and pull it out into a new pile that's at level 2, which is between person random slope differences. So now there's 3 different things to be explained. Why do some people start out higher or lower? I don't know, because of their group, their whatever, time constant characteristics. Why do some people grow more than others? I don't know, because of something about the person. And then beyond that, why doesn't the trajectory fit all of the data perfectly? Like, why are there still differences between what the trajectory says and what each individual data point has? Why are you off your line today? And the only thing that can explain the latter is characteristics that change over time. Level 1 predictors. So when all is said and done, we have 3 different models happening at the same time. Models predicting why some people start higher than others, predicting the random intercept. Models predicting why some people change more than others, predicting the random time slope. And then models predicting the leftover within person variance, why are some occasions worse than predicted. So in the first week of this class, I talked about regression lasagna. That's where we're at here. So it's like there's 3 outcomes being predicted at the same time. That's where we're headed with this.
Wait, I have a question. So if you take, so you're taking that between person random slope differences from the within person pile?
Yep, that's where they come
Okay.
from.
Why I'm having a hard time. I'm trying to figure out how that comes from within person.
These aren't great pictures to illustrate that point,
Okay.
but that is what's going to happen. Because once upon a time, everything was in level 1E, and the role of multi-level models is to pull out as many different sources of person variance as are needed to fully capture all of the patterns of correlation in the data. So everything came from E at one point in time. So this additional relationship in terms of how people can differ from each other that's implied by a random time slope, that is another kind of person dependency. It predicts a correlation of occasions from the same person that changes over time because of differences in change. And it predicts variance that changes over time as well. So it's a new pattern that we're going to be building into. But not until next week, because we're out of time for today. So any questions more before we wrap up? We will revisit this next time and get to see how the model progresses step by step. All right, then just as a reminder, next week we do not have class on Tuesday because that's spring break. Enjoy. So I will see you a week from now on Thursday. Let me know if you need anything. Homework 1 is due next Thursday in a week. You should be able to do all of it, and if not, let me know if I can help. All right. All right, then office hours start now. See you all next week.